From the beautiful South Studios of Way Happy, this is Mr. Meyer and 2-1, the derivative and the tangent line problem. So in the book, 2-1. But what we really want to talk about is the tangent line problem and start getting ready for some serious calculus fun. So let's talk about maybe you're driving your car, and this graph to the right, graph to the right is represented you driving your car and you're getting on the freeway. And so, I'm going to put time across the bottom here. This is going to be time. And as time increases, your speed increases. And hopefully, unlike this graph, this is just a little portion. I don't want you to go speeding off ridiculously high rates as you get on the freeway. So be careful. The thing we can do when we do this is, over as the time went on, your car was traveling faster, faster, faster. I can find what we've always called your average rate of speed. I could get at a certain point in time, I could find it, and I could get another point in time, and then I connect that with a line. And what I'm actually doing there is I'm finding your average rate, the average rate at which you traveled, right? And so say, whatever, however fast it was for however time it was, that's how fast you went over average. And that line that we just created, that blue line there is called a secant line. This right here is called a secant line. And a secant line, just by definition, is, intersects the curve through 2 points. And that secant line will give us your average rate of speed, right, for that time. Now, here's what's kind of cool. As I make this smaller and smaller, say I want to know, like, I take this point here, the second point, and I slide it closer. So now the secant line's like this. And then I slide it closer, and now the secant line's like this. And now I slide it closer and closer and closer. I'm getting really close to what's called the tangent line. In fact, if I keep getting closer and closer and closer, I'll get the tangent line, right? Because I can go infinitely close. In fact, limits help me get infinitely close to the 2 points. So that, my friends, is what the tangent line problem is all about. It says we can take a secant line and try to get it closer and closer to a specific point. And why would I want to know the tangent C at this point right here, say? Because that'll tell me how fast you were going at that time, right? That'll be your velocity at that time, if I can get really, really close together. So the whole plan here is to find what we call slopes, right? And so slopes that you've been doing forever, they've just always been this weird fraction, or maybe not, but they've always been this weird fraction of rise over run. That's still going to be the same case. Now, let's get kind of generic on this, right? So if you look at the rise over run, if you kind of figure out that this point right here is point C, and then if you plug it into the equation, you get the y value, that would be called f of C. And then if I take this arbitrary distance, we'll just call it delta x, that this new point right here is going to be C plus delta x, because however far it was, delta just meaning the change in x, right? So maybe it was 1 unit, maybe it was a half a unit, maybe it was 0.000001 unit. That would be awesome, and we're just really zoomed in. If that's that, then the y value of that would be C plus delta x. And so if I want to find the slope, then what do? Well, that's what this part next to it is. You would subtract the y values. Remember, you do y2 minus y1. That's this part right here, right? So the rise of this graph is f the blah, or let's just call it change in y. And then to find how far we ran, well, we know how far we ran delta x, or you would take this guy and subtract this guy, and you would get delta x. So what we're getting at is that as we make that delta x really, really small, let's try to get it really small so we get 2 points that are really close. Like, so now pretend that this graph is really zoomed in. We get 2 points really, really small. Eventually, we should be able to get the tangent line and not the secant line. And that's what we're going to try. And so like right here, look, if you look down here, you can see slope is just the change in y and the change in x. So if we can get closer and closer and make that distance between the x's, make that delta x, if I can make that 0.000000000001, right? Then what am I doing? I'm really finding the limit of, as x approaches 0, of the change in y over the change in x. And that will give me the tangent line, which will give me your velocity at that time. How crazy is that, right? So we're going from taking your average of your whole trip, like we did in pre-calc, to shrinking this distance down really small. And now I can tell you exactly how fast you were going at that point. And we call that a point of tangency. Like if I wanted to find this point of tangency right here, this is where I would find the tangent line. And I can tell you how fast you were going at that moment just by finding the slope. That slope, say it looks like 1, you're going 1 mile an hour. But look up here. When we get here, the point of tangency is going to be like that, almost vertical. Now you're going like, that has a slope of like 90. Now you're going like 90 miles an hour, right? So it's crazy how quickly you've changed. But over time, if the secant line is really, if you have a secant line, then you're just going to get an average. But this is going to be an instantaneous. All right, that was a lot of yapping. Let's see if I can let's test it out. So I have this equation, right? The slope, and maybe I'll even draw the picture just to make it a little more clear, or maybe not. Go down 3, right? And you go up 2/1. It's something like this. It's like this. And so I'm saying at point 2, right here's point 2, right? When it's 2, I want you guys to help me find the slope at that point. So what would we have to do? Well, we're going to have to pick a random delta x out here, however far. Now, I really want to be zoomed in, so this is really, really close to 2, but I can't do it with my pen, right? So here is that distance. So this distance right here is going to be f of 2 plus delta x minus f of 2. Think about that for a second, right? I just took we plugged in the value of this guy, which is 2 plus delta x, really, minus this guy. And then we plugged it in, they gave it the y values. That's why I'm using f. And so it's just y2 minus y1. Most of you think of this as y2 minus y1 over x2 minus x1. Now, if I want to do that, right, then I know that this distance right here is delta x because that's what it's labeled. But if you wanted to see the math, you'd be like, oh, that's over, now what is that? 2 plus delta x minus 2. And so the 2's would cancel, and that's why we just put it over delta x. All right, let's see how this works. I'm asking you guys to find the limit as delta x approaches, as delta x approaches 0. We get really, really close together. F of 2 plus delta x minus f of 2 all over delta x. Whoa, why did I change to green? That's kind of, all over delta x. My pen does not want to write. All over delta x. And it's highlighted green for no apparent. So now think of this. That, my friends, right there is what we need to figure out. And we've seen that before, right? When I made you do limits. And I said it had something else to do with derivatives, and it does, but we'll talk about that after. So let's see. Let's find out what f of 2 plus delta x is real quick. That is 2 times x plus delta x minus 3. So I substituted that in. Oops, that was supposed to be a 2 plus delta x. So let's put that in. 2 times 2 plus delta x minus 3. Now minus f of 2. So let's plug in f of 2. When I do that, I get 4. I get 1. So I don't care if you, I don't hope you don't mind that I did that. All over delta x. And oh my gosh, I'm still trying to find the limit as delta x heads to 0. All right, let's try to clean that up real quick, because if you plug in 0, you're going to probably get 0. I don't know, what do you get? 4 minus, you have 4 minus 4 over 0. So you get 0 over 0. So do something else with this limit. How about 4 plus 2 delta x's minus 4 all over delta x? If I clean that up a little bit. And last but not least, I think you can see what I can clean up there. The limit as delta x heads to 0 of the 4's canceled. 2 delta x over delta x. Oh, good golly. The delta x's cancel. And you have the limit as x of delta x approaches 0 of 2. Wait, there is no delta x in there. So the limit is 2. Or the slope is 2 at that point. And then we laugh because we say, wait, we knew that already. It was the equation of a line who had a slope of 2. But we just proved that using this, shrinking closer and closer, making a really small delta x, we got the instantaneous, we got the instantaneous speed. And now I'm like, okay, go away. I am going to say, hey, the slope is 2. All right, let me ask you a question, and we'll be right back. All right, nice work. Now, smartly enough, I've turned on my mic, so I should sound a little better. um, Here we go. This was a link I had in the notes there that said "show this," and it's showing that there's a graph, the blue graph, sine, sine x of plus 0.3x, and there's a secant line, the red line. And so that red line is the secant line. And just to kind of show you how cool this is if I pull that secant line closer, look at the 2 points over there. I'm sliding it closer and closer. The distance, that delta x is getting smaller and smaller and smaller. Look what's happening to the red line. It's really becoming a tangent point, right? It's really becoming, those 2 points are so close together that it is actually becoming a tangent point now. And then I can do something fun like I can tell this now. Desmos has all these cool things where I can hit the play button and it'll move those points along. And you can see the point of tangency is constantly changing, right? So look at that slope. It's really positive. Oh, now it's negative. Oh, wait, it's positive again. Oh, wait, now it's negative. Oh, it's positive. So this is representing something that's bouncing back and forth. It has a positive slope and it's speeding up and slowing down. So it's beautiful. And that's what's so cool. Something as simple as slope is now defining how fast something's traveling. And if it's traveling at a velocity that's negative or positive or really steep or not so steep, kind of slowing down. I mean, it's insane. So I just wanted you to see that because I thought that was truly a little amazing thing there on Desmos and our friends there. All right, what have we done? We have done a very big step. We have now just kind of written the definition of tangents of a derivative. The way you find a derivative is right there in that box, right? And you take the function and you evaluated x plus delta x minus f of x. What is that really? That's really y2 minus y1 over the change in x, x2 minus x1. That's all derivatives are. They are the limit as delta x approaches 0. So you get infinitely close. You get infinitely close to these 2 points being close together. These 2 points are next to each other and they are so close together that we're headed towards 0, right? But we can't be headed towards 0 because dividing by 0 would be non-existence. That's why we had to use this thing called limits. And that's what a derivative is. The way the derivative is written, you can see here is f prime. And so the super important equation that you need to know is right there. This one guy right here. That is your definition of a derivative, right? Now, some books don't like the delta x. Some kids don't like the delta x. Some people don't like the delta x. So they write it like this, right? They change the delta x to an h. That's awesome. You can do that. Have a good time. So you don't have to worry about anything. But what that will give you the derivative, and that will give you the slope. And that slope will be the instantaneous rate of change, right? That is exactly how fast you are changing at that. And this is called finding derivatives or differentiation. The way we write that, and here's probably another super important point, is we call this thing f prime, the derivative. If you have function f, then f prime is the derivative. So f prime of x, right? Other things people will do, they'll call it dy dx, right? Right there you can see the dy dx. They will call it y prime. They will call it d dx, right? And leave that other one. So those are all notations for derivative, all that are there and common and fun. All right, so this is the last one I want to do right here. I want to do this one right here on the notes and say, all right, let's use this definition of derivative to find the derivative of this. Now, what does that mean? I want to find the derivative, which is going to be an equation, and then I can tell you the instantaneous rate at any time, right? So here we go. First things you want to do when you're asked to find the derivative using the definition of derivative, all you have to do is say, all right, I got to figure out what f of x plus delta x is. So that would be going into this equation. It'd be x plus delta x cubed. Oh no, that's not going to be good. Plus 2 times x plus delta x. Right? And if you want to clean that up, I might as well. Let's cube it. Oh my gosh, what is it going to be cubed? For those people who remember Pascal's triangle, 1, 3, 3, 1, right? And then it was x cubed, x squared, x, and no x's. And then no delta x's, delta x squared, and delta x cubed. All right, there's all the terms. So it will foil out. You foil it out however the heck you want. But you should get x cubed plus, oh, where did it go? I love it when my pen changes on me because this thing likes to be grumpy. Plus 3x squared delta x plus 3x delta x squared plus delta x cubed. So that was the foiling out of this to the third power, plus 2x plus 2 delta x. So that is that. All right, now use the definition, right? So according to the definition, we are now going to do this definition and find the derivative. And the derivative will be an equation that will be able to give us the slope at any given time. So here we go. I need to do this thing, which is what we just did, right? So it's the limit as delta x heads to 0 of all that stuff, x cubed plus 3x delta x. Oops, I forgot the squared. Plus 3x delta x squared plus delta x cubed plus, well, where's it going? Plus 2x plus 2 delta x. So that was all of that, right? And then minus f of x. Well, f of x we know, it's right here. It's x cubed plus 2x. Now it's minus, so I better use parentheses, x cubed plus 2x. And then all over, that was the rise, and now the run all over delta x. And we want that run to be 0. That's why we're doing the limit. All right, so you plug in 0, and you might notice that you're going to get 0 over 0. And you're like, son of a gun, we got to do something else. All right, let's do something else. So I start trying to do some algebra, right? Like I noticed this x cubed cancels out with this x cubed because it gets subtracted. I noticed that this 2x gets canceled out with this 2x because it gets subtracted. So that's feeling pretty good. The next thing I notice is that everybody has a delta x in them. That's weird. Or not really. That's convenient, really. So let's factor it out, right? Let's factor that out. So if I factor it out of there, I'm going to have delta x, but then what would I be left with? I'd be left with 3x squared, and now we factored out the delta x, plus 3x, and then there's 2 delta x's there, so there's still one left. And then delta x squared, and we factored out that, plus 2, we factored out the delta x, so it looks like that, all over delta x. And good news, that cancels again. And you're like, yay, now we don't have 0 over 0 anymore. Life is good. We have as delta x heads to 0, we have 3x squared plus 3x delta x plus delta x squared plus 2. We have that. And I can find the limit of that. I'm going to put delta x as 0. As I put that in, this goes to 0, this goes to 0, and I am left with the answer 3x squared plus 2. And what is that? That is the derivative. You could call that f prime of x, right? You could call that dy dx. You could call it whatever you want, right? But that is the derivative. And what does that do? That equation tells me the slope at any given point. If you want to know when x is 1, you plug a 1 in and you get 5. The slope is 5 when x is 1 of this graph. So this graph right here, graph it. Look at x is 1, the slope's 5, right? Look at x is 2, the slope is what? 14. So, oh my gosh, it's so much steeper, right? And say that represented your speed or something like that, then I could see how fast you were traveling instantaneously at every moment. So that is the definition of derivative. How insane is that? All right, let me ask you some questions. I'll see you tomorrow. Stay happy.